Hi, this is Mr. G coming back to you guys with an ions video. So we talked briefly about valence electrons, and now we're going to take a look at what happens when we lose or gain those valence electrons. So what an ion is it is a charged particle. So it can have a positive or a negative charge depending on whether it loses or gains some electrons. So remember that atoms are neutral. So their positively charged proton number is equal to the negatively charged electron number, meaning that the overall difference between positives and negatives, if you were to add them together, would be zero. So it doesn't have a positive negative charge. With ions, because you're changing the number of electrons, your proton number won't change, so you're just changing your number of electrons. They will no longer be the same. So your overall charge can be positive or negative, depending on if you've gained or lost electrons. So if we were to take a look at an example, we're going to use sodium as our example. And I've drawn out sort of three scaffolding things to help us with this example. So we'll start on the left here, where I've drawn that arrow, and just draw what a sodium atom would look like. So it has 11 protons, and it's neutral, so it's going to have 11 electrons. We can fit in the first energy level 2 electrons. The next energy level, the second one, will fit 8. And the third energy level can fit 8 electrons, but if we only have 11, that means we just have 1 electron remaining. So our valence electron in sodium is that single lonely electron. Okay, we always think to ourselves, if we draw the atom and we think, what sort of ion would this form? We think to ourselves, is it easier for that atom to gain electrons to get to 8, or to lose an electron so that it can drop to its lower energy level and be full and happy and what we would say is stable? Okay, so in this case, we're going to look at the atom changing into an ion. So we have those 2 electrons, we have these 8, and we thought to ourselves, this lonely electron, it's a lot easier to lose that electron than it is to gain 7 more. The only thing we need to add to an energy level or a Bohr diagram is we add square brackets, and then up here in the top right, we put the charge. And sodium has a positive 1 charge. The reason this is if we look down here at the proton number, we now have 11 positives. And if we count our negatives, we only have 10 negative electrons. So if we were to compare these two, we now have 1 additional positive molecule. So it carries a positive charge. The reason neon is over here is we generally like to compare these diagrams to the nearest noble gas. So if we look at the energy level diagram for neon as an atom, well, it doesn't form ions because it's noble and stable. It now resembles what a sodium ion would look like. So that is how we know and we can compare. If it resembles its nearest noble gas, then we know that it will be stable as an ion. Let's take a look at another example. So this time we're going to take a look at fluorine. If you take a look at the periodic table, fluorine is actually on the opposite side of neon than sodium. So they're quite close. If we take a look at the sodium atom first, again, we have 9 protons. So we should have 9 electrons to make this a neutral atom. So we're going to fit 2 in the first energy level. And the second energy level can fit 8. But if we only have 9 electrons, that means that we only have 7 remaining. So we're just going to write those in there. Again, we take a moment to consider, we could move down an energy level and be stable, but we would have to lose 7 electrons in total. Or, if we already have 7 in our valence shell, would it be easier to gain just a single electron? In this case, it is much easier for fluorine to gain that single electron. So we have 2 electrons at first, and then what we like to do is gain an electron from something like a sodium ion to have a nice full second energy level of 8 electrons. Again, to complete this diagram, we want to draw square brackets around it. And then on the upper right-hand side here, we just want to put a negative symbol to display that we do have a negatively charged ion. If we, again, compare the positives and negatives of this ion, we have 9 positives. And now we take a look, we have 10 negatives. Okay, so if we were to add those up, we have just a single extra negative. Okay, so this is a negatively charged ion. Just quickly comparing to neon, again, if we look at neon, even though it does not form ions, has this stable configuration. So when fluorine forms this ion, it will no further react with other things. It's happy with that gained electron that it has, and it will stay in that stable configuration. Just one other thing I'd like to add before I finish up this video is some terminology that we often see with ions. So with positive and negative ions, we actually have different names for them, and I'll give you guys a little trick to help you remember. So negatively charged ions are often referred to as anions. My personal favorite little memory trick is it almost looks like they're onions, and onions are negative. Nobody likes onions. If you like onions, you're a liar. Some other people don't agree with me, so sometimes we think of an antagonist in a book or a movie. Okay, they're usually the bad guy, so they're the negative. With positive ions, we call them cat ions. I purposely did the T like this because it's a big positive symbol. Okay, so cations have positive in them, or you can try to remember it because cats have paws. I spelled it that way because it's short for positive. Okay, so often you'll see anions, those are always negative. Cations, those are positive. So that's just a little trick to help you remember.